Okay, so last time we talked about stability analysis using Lax-Wendroff. We proved that to be stable we need to have alpha less than 1, otherwise the magnitude of C goes larger than 1. So I showed you a Matlab script that you can use to look at the stability of Lax-Wendroff. So let's look at that script again. The result of that script is the following. So we get this graph for 3 different alphas, alpha 0.8, 1, and 2. I think that might be a typo. This should be alpha equals 1.2. So let me just fix that. So it has to be 1.2. Okay. So you can also, so the blue line is alpha equals 0.8, red is alpha equals 1, and then black is alpha equals 1.2. I also have another line here which is dashed black, so if you can see it's really difficult to see, but I can see it over here. It's the dashed black line which is exactly over the red one. This is where magnitude of C is equal to 1. So anything within this circle has magnitude less than 1. That means this blue has magnitude of C less than 1. Red is included because it's right on the circle, so the magnitude of red is less than 1, but then black has magnitude bigger than 1. So we conclude that for alpha less than or equal to 1, the magnitude of C is less than 1, and that is the stability condition, or the condition for stable Lax-Wendroff is alpha less than 1. So Lax-Wendroff is conditionally stable. Alright, so now what I'm going to show you is a Matlab script that we can use to see the solution of advection equation using Lax-Wendroff. So basically I implemented this equation in Matlab, and we're going to look at one example where we have a half cosine wave propagating from one direction. We're going to look at how we can solve Lax-Wendroff using that. So this is the script for Lax-Wendroff. So we know that it's second order in time and second order in space, as I mentioned here. So initially we set up the variables as before. We're not going to go over them, we're going to skip over them. Alright, so then we create a t vector, x vector, we create a mesh grid, which is our space-time coordinate. We set alpha, and then we initialize. Alright, so actually I'm not using half cos wave, I'm using heaviside function, doesn't matter, but there's another option here in the code you can download from Blackboard and play with it. So if you put initial condition of type 1, then you get half cosine wave. You put initial condition of type 2, you get a heaviside function. Alright, so let's see, for this heaviside function, this is how we implement this. Is like 2 lines of code. This is un plus 1 at xi is equal to u at n at still xi, and then we had this we had the average term where we have it over here. So that's the second order in alpha, and then we had a term with first order in alpha times ni minus 1, ni plus 1, ni minus 1. So that's exactly corresponding to this equation. We have an alpha, linear in alpha, second order in alpha, and then we calculate everything, we get n plus 1, we get the variable at n plus 1 and xj. Alright, so using n and j plus 1 and j minus 1, we get n plus 1 and j. And that's what we have here. Alright, and the rest is just having different snapshots or maybe create some animation. Okay, so if you run that, so initially it was a step function. You can think of a plug flow, like concentration is high here and suddenly is 0. And then as you increase the time steps, then because velocity is positive, there's a flow from left to right, so this step function should move from left to right. So now you see that we get some weird oscillations behind the wave, but the thing is, because alpha is less than 1, this oscillation doesn't grow. It becomes initially it grows a little bit, but it's gonna stay there. So it doesn't increase in time, which is good. So that means the stable method, and that's why because we're using alpha less than 1. Now, what if I increase alpha to something bigger than 1? So I'm gonna uncomment this line. So this is, so for now we got alpha 0.4. Now if I run the code with this new v, or we increase the velocity a little bit, then our alpha is negative, but still less than 1. So this time we get these spurious oscillations behind the wave. Okay, so anyway, so if alpha less than 1, we get some spurious oscillations, but the oscillations won't grow. Now let's increase the velocity to something which leads to an alpha bigger than 1. So I'm going to stop this, run it. Now you see alpha is slightly bigger than 1, and now you begin to see the oscillations grow in time. So if you run this for a longer time, basically those oscillations will dominate the solution and you don't get anything out of it. So this is to prove that, alpha is equal to 1, the condition on stability is actually correct. Alright, I'm going to stop that before it kills my Matlab. Okay, so let's go back to the notes. So we talked about stability analysis of Lax-Wendroff. We showed you some example on Lax-Wendroff. Now I'm going to talk about boundary conditions. So we are moving to page, oh by the way, before actually talking about the boundary conditions, I wanted to just summarize the methods we learned so far with the stability conditions. So we talked about upwind, we know that it's first order in time, first order in space. This is the condition we got for amplitude of c, and for this thing to be less than 1, we have to put actually this guy to be less than 1, and we realize that we got condition in this table. I think alpha less than 1 was the thing for upwind. Yeah, so and this is the discretization equation. Depending on whether alpha is positive or negative, you have to use plus minus here, and then you have to go forward backward in space. So we talked about that because we said upwind is really dependent on which direction the flow is coming. We talked about forward turn time sent on the space. It's first order in time, second order space. This is the condition for c, which has to be less than 1, and we argued that this thing is actually unconditionally stable, because for any alpha we put in here, this is always positive. 1 plus any positive is bigger than 1, so this thing is always bigger than 1, and regardless of what you use, this always diverges. Okay, the next thing we looked at was Lax-Friedrichs, which is first order in time, second order space, which is similar to forward in time, center in space. But this method is conditionally stable, and we find some alpha for it. Can't remember what it was, but certainly for some alpha this is less than 1, and this is the discretized equation. Okay, where alpha is v del t over del x. We talked about leapfrog, and we showed that for alpha, I think less than 1, the method is always stable, and c is exactly equal to 1. This is the discretized equation we derived for leapfrog. And then lastly, we talked about Lax-Wendroff, which is second order in time, second order space. So we see that the order of accuracy increases from top to bottom. And then we realized that this is also conditionally stable for some alpha less than 1, and we had the discretized equation right here. All right, so now here I have another table for different stencils for derivative with respect to, this is the first derivative. You can think of first derivative with respect to x. So here I'm summarizing forward Euler, which is j plus 1j. So these are just, these are not partial derivatives. These are just derivatives with respect to one variable. Backward Euler, where we have jj minus 1. These are first order. Then we have the second order version. For second order version, we have forward difference, backward difference, central difference, where we use 3 points for forward and backward, and we use 2 points for central difference. So keep that in mind, these are second order. Then we can also derive fourth order in del X, which is even more accurate than these guys. And so you see that for fourth order, we need to know 1, 2, 3, 4, 5. Also for every calculation, we need to know 5, or we're using 5 variables. At j, this is forward, so I'm going to use j, the one next to j, the one next to j plus 1, the one next to j plus 2, and the one next to j plus 3, with different coefficients. Similarly, I have same thing for backward Euler with different coefficients. Again, 5 terms here. And then we also have central difference version of that, which uses 4 terms. And you see it's symmetric. You have j plus 1, j minus 1, j plus 2, j minus 2, j plus 1, j minus 1. All right. So here's another table for the second derivative. This one was the first derivative. The next one is for second derivative. We can have forward, backward difference. So this is first order. We can have second order, and we can have fourth order family for forward, backward, central difference. The only thing that doesn't have central difference is the first order, because central difference minimum has second order accuracy. I also included the third derivative for forward, backward difference, first order, and then forward, backward, central difference for second order. Here is a table for fourth order derivative in space. These are useful sometimes because if you run into a fourth order differential equation, you want to use these discretizations. Again, for first order, we have forward backward Euler, and then forward backward central for second order in space. You can actually change these for time derivatives. In case you have second order or first derivative in time, you can just replace x by t. All right. So now we're going to talk about boundary conditions. So far we talked about how to solve differential equations using, different schemes: upwind, forward in time, central in space, leapfrog, Lax-Wendroff. Now we're going to talk about boundary conditions. So the first thing is periodic boundary conditions. In periodic boundary conditions, you can think of if there's a flow going from left to right and hits the right boundary, it has to come back and show up again from the left side. So basically we have to create a loop. Everything goes from the right side, shows up from the left side again. So let me show you one example of periodic boundary condition using upwind. This code is on Blackboard, so you can use and you can go ahead and download and use it. So for periodic boundary conditions using upwind, to upload this file. Alright, so this is upwind using boundary conditions. Okay, so let me run that and see what happens. So if there's a wave or flow coming from right to left, when it hits this boundary, it has to show up on the other side. So this is pretty much like a loop. It's like connected from the so x equals 0 is connected to x equals 5 in this case. Anything goes out comes in from the other side. So it looks like there's a periodic wave going through this medium. Okay, so now let's see how we can implement this. I think it's very easy. If you're sitting at the last point, anything ahead of that point should be actually looped back to point 1, and for all other points, anything ahead of the point is just I plus 1. So for any point I, you have I plus 1. For when I is equal to NPTS, the next point is just point 1 because it loops back. And similar thing is if you reverse the direction of the velocity. All right, thanks a lot for watching.